Okay, so let me also write this product measure this way. So dx0, dx1, all the way to dxn. So how do we calculate it? So we start from the first space. So given our position in the first space, we go to the second space, space number 1, using this kernel. Now, given our positions at times 0 and 1, we use this measure to land in space number 2. Given our positions in spaces 0, 1, and 2, this is the measure that we use to land in space number 3. And finally, given all our positions, the whole history, this is the measure we use to land in the last space. So if you write it in this notation, using this notation, it looks more intuitive, I think. When you write it down using giant multiple integrals, it looks kind of ugly, but this differential notation makes it kind of more intuitive for me, at least. Of course, this is going to be more meaningful and intuitive when we talk about conditional distributions. So right now, we don't know anything about conditional distributions. But these are going to become the conditional distribution of the last component given the components from 0 to n minus 1. So one special case is when you have just free coordinates. Let's just look at the product of E0, EI, script EI, and nu I. So you have pi equals nu 0, nu 1, nu n. Okay? Or pi dx0 to dxn is nothing but nu 0 dx0 to nu n dxn. So you have just measures on each space, and this is the product measure of them. In other words, you see those nu 1, nu 2, etc. as kernels that are trivial in the sense that they don't depend on the past. Okay? So K1 is just a measure here. Okay? No dependence on this space. And K2 is a measure here, no dependence on those two spaces in this special case. So you can view it as a kernel, which is trivial in that sense. So this construction allows you to talk about such product measures, products of individual measures. And for instance, this pi assigns to let's say a measurable rectangle what? The measure of the first, measure on the space 0, measure of the set dn in space number n. So where this is a measurable rectangle. And there is a further special case. Just take all of them to be the real line with the Borel sigma algebra and the Lebesgue measure. Let me now make it from 1 to n, okay? I don't want to call it n, or let's say n minus 1, 0 to n minus 1. Okay, so this is what? This is the n-dimensional space with the Borel sigma algebra and the Lebesgue measure on dimension n. So the product of Lebesgue by itself n times is called the Lebesgue measure Rn. So Lebesgue n dx0 to dxn minus 1 is just dx0 to dxn minus 1, because this is the notation for Lebesgue measure on the real line. So for instance, if you have, let's say, f x0, x1, x2, and you need to integrate it with respect to the Lebesgue measure on the three-dimensional space, let me write just dx for this. So you can write it as a triple integral, right? But the order is not important, thanks to Fubini or Tonelli, whichever applies. Let's say f is just positive measurable. So if you have the one-dimensional Lebesgue measure, this is just length, right? Notional length. If you have the two-dimensional Lebesgue measure, this is just the notion of area. So if you have a rectangle, you calculate the area of it by this formula for measurable rectangles, right? If you have the three-dimensional Lebesgue measure, this corresponds to volume. Of course, generalized volume, because you can also talk about the Lebesgue measure of crazy sets. And it gives a meaning to the notion of volume, which we usually learn for simple geometric structures, right? Cubes and spheres and cones. But it actually makes sense with the Lebesgue measure. It makes sense for just quite ugly sets. And for higher dimensions, we just call it hypervolume. And we cannot draw a picture for these cases. So one definition I'd like to talk about is the continuity of a random vector. Okay. So do you remember the definition of a continuous random variable for the real valued case? When do we say that a real valued random variable is continuous? Remember, we talked about discrete and continuous random variables, and that was all about the relationship of the distribution with respect to some other measure, right? So if it is absolutely continuous with respect to some counting measure, we call it discrete. If it's absolutely continuous with respect to the Lebesgue measure, we call it continuous. So since we have a multidimensional Lebesgue measure, we can talk about continuous random vectors, right? So random vector x, let's say 1 to n, is called with values in Rn, is called continuous if its distribution is absolutely continuous with respect to the Lebesgue measure on Rn. Remember how we write it this way, right? So since this is a sigma finite measure, maybe I should have said Lebesgue n is sigma finite. just like the one-dimensional case. So since this is a sigma finite measure, by Radon-Nikodym theorem, so if X is continuous, then by Radon-Nikodym theorem, density, let's say G, which is the density of the distribution with respect to the Lebesgue measure, exists, and it is unique up to Lebesgue almost everywhere equality. So in other words, we can write the distribution of the vector as g x1 to xn, dx1 to dxn for some function g, and this is called the, again, the probability density function, or sometimes joint probability density function of the components. For instance, the example that we did at the beginning today, so let's say pi dx dy was given as this. This was an example of a continuous distribution on R2, or let's say R plus cross R. So the random variable xy with this joint distribution is continuous. And this is the joint probability density function of it. But let me give as a remark one warning. So if x is continuous, then each xi is continuous. Well, why? Because you can just integrate it over all the variables but the first one. Then this is going to be the distribution of the first component, right? This is what we did in the example. So if you have a joint PDF, you just integrate it with respect to the second variable to get the distribution of the first component. So if you have a jointly continuous vector, the individual components are also continuous. But not the other way around. The converse is not true in general. I'm not going to give an example for that, but maybe I can provide an exercise later. So you can construct random variables that are individually continuous, but together they don't form a continuous random vector. Okay. So I guess that's it about random vectors. And now we're going to talk about a very nice, important probabilistic concept, and this is independence. Okay? You have seen one form of independence in the midterm exam, and that was about independence of sigma algebras, right? So indeed, the way we're going to start talking about independence is going to be through the independence of sigma algebras. And then we're going to define the independence of random variables in terms of the independence of their generated sigma algebras. So independence of sigma algebras is the starting point. And if you want to pass to other concepts like random variables, etc., random vectors, you can always talk about the independence of their generated sigma algebras. So we're going to start by defining the independence of sigma algebras. Okay? So this is the third section of this chapter, independence. So it is an entirely probabilistic concept. It doesn't make too much sense in measure theory, in general measure theory. So we're going to work on a probability space, no abstract measure spaces anymore, be a probability space. So here's the definition. Let's say before the definition, let F1 to Fn be subsigma algebras of F, where n is some finite number. So what is subsigma algebra? Subsigma algebra is a sigma algebra that is smaller than the big sigma algebra. So they're all subcollections of F, and they're all sigma algebras. So we say that F1 to Fn are independent if you take an F1 measurable random variable Z1 and an Fn measurable random variable Zn, the expected value of this is equal to the expected value of the first times the expected value of the last. For all F1 measurable positive random variable Z1, Fn measurable positive random variable Zn. So you can take indicators of events in F1, F2, etc. You can look at more complicated things. For instance, you can take simple positive functions that are F1 measurable, F2 measurable, Fn measurable. You can take positive measurable functions, namely just positive random variables. So Z1 measurable with respect to F1, Zn measurable with respect to Fn, etc. And you have this product rule. Okay, you have this product rule. And this is probably not the definition you've seen in other places. So let's relate it with other definitions, other possible definitions, namely characterizations of independence. For instance, is this equivalent to the definition of independence in the midterm? Right? So we're going to list some equivalent properties. So the following are equivalent. Number one, F1 to Fn are independent. Number two, you can replace those random variables with bounded measurable random variables. For all F1 measurable bounded random variable Z1, Fn measurable bounded, which can take negative values, of course. Let me write it this way. Number three is the definition in the exam. So you have A1 intersection AN is the product of the probabilities of individuals. For all A1 in F1, AN in Fn, and there was a version with pi systems. So let me write it this way. So for all A1 in some pi system that generates the first sigma algebra and some pi system that generates the last sigma algebra. And we also need to consider the full space. So where S1 is a pi system on omega such that it generates the first sigma algebra, and Sn is a pi system on omega such that it generates the last sigma algebra. Dependent means what? We have this formula for all positive measurables Z1, Z2, Zn that are coming from the right sigma algebras. So if you look at number 3, this is the same expression but with indicators, right? So if you take this to be indicator of A1, indicator of An, this is going to become the probability of the intersection of A1 to An. And this is going to be the probability of A1. This is going to be the probability of An. So 1 implies 3 is easy, right? Just special case. And also 3 implies 4 is even easier because those pi systems are, of course, subcollections of the full sigma algebras. So if you just, so if you have A1 in S1 or A1 equals the full space, it is always in F1. So 4 is a special case of 3 and 3 is a special case of 1. So clearly 1 implies 3 implies 4. So let's prove the equivalence of 1 and 2. 1 implies 2. Well, I will prove all of these for n equals 2. We don't need full generalities in all proofs. So let's do everything for n equals 2 to avoid writing induction proofs. Okay, n equals 2. So 1 implies 2. 1 implies 2. In 1, we have positive measurable functions. In 2, we have bounded random variables, which might take negative values. So we're going to, since we're going to prove 2, let's take 2 random variables that are bounded. So let Z1 be a bounded F1 measurable random variable, and Z2 a bounded F2 measurable random variable. So we're going to calculate, we're going to prove that the expected value of Z1 times Z2 is the product of the individual expected values, assuming number 1. Assuming number 1, which has positive random variables. So we all know that this expectation is defined as the expectation of the positive part minus the expectation of the negative part, right? So this is a way to pass to positive things. Now, what is the positive part of Z1, Z2? Well, we have to look at the signs of Z1 and Z2, right? When do we have positive sign for the product? When is the product positive? When is the product of two numbers positive? Both are positive or both are negative. So this means we can write Z1, Z2, the positive part of Z1 times Z2 as the positive parts multiplied or the negative parts multiplied. And similarly, this is the opposite. So they have opposite signs. And now we have positive things, right? These are all positive random variables. So by 1, we can separate everything. It is so confusing to write it down correctly because there are plus and minuses here and plus and minuses there. So I have to be careful. There should be a plus here. First mistake. Okay, Z1 minus times Z2 plus. Okay. So now all you have to do is to group them in a good way and show that this is equal to expected value of Z1 times expected value of Z2. Right? You can maybe group this with this, and then this with this, which is going to give you expected value of Z2s, and then you do it one more time, you get the expected value of Z1. Okay. So how about 2 implies 1? So this shows number 2, right? Exactly as we desired. So number 2 is for bounded measurable. Number 1 is for positive measurable. So we should take positive measurable things, right, to prove 1. So let Z1 be a positive F1 measurable random variable, and Z2 a positive F2 measurable random variable. So now we need some bounded random variables. Okay? Can you come up with some bounded random variables? If you're given some positive measurable random variable, can you associate some bounded random variables to it? You don't have to come up with just one. You can have a sequence of them. So are simple positive functions bounded? Of course, right? A simple positive function just takes finitely many values. So take the largest value, it's a bound. Right? So we can approximate those positive measurable random variables by their approximating sequences. But they don't have to be the standard ones. Just take an arbitrary simple positive function sequence converging to Z1. So there exist simple positive Z1 and Z1, sorry, Z11, Z12, etc., converging to Z1. And let me say simple F1 measurable. And there exists simple F2 measurable Z21, Z22, converging to Z2. And we have each Z1 and Z2n are bounded. So Z1n times Z2n is equal to expected value of Z1n, expected value of Z2n. And this is by number 2. By 2. We have it for, let me not write each. We have by number 2 that this relationship holds because Z1n and Z2n are bounded random variables. So all we have to do is to let n go to infinity. And by using monotone convergence theorem, since we have monotonicity, this product also goes to what? Z1 times Z2, right? If you have one sequence converging to Z1, another sequence converging to Z2, their product, the product sequence converges to Z1 times Z2. The limit of the individuals also converge to the expectations of the original random variables. So we get expected value of Z1, Z2 equals expected value of Z1 times expected value of Z2. So we proved 1 implies 3 implies 4, and 1 and 2 are equivalent. What we're going to do is to show 3 implies 1 and 4 implies 3, and we're going to be done. So let's prove 3 implies 1. So 3 is for indicators. So note that three means we have expected value of the product of those indicators is equal to the expected values of the individual indicators. Well, I was going to do it for n equals 2. Let me not confuse you. Let me just write it for two things. So using linearity, we may extend it to simple positive functions, simple positive Z1, Z2. And using monotone convergence theorem, we may extend it to positive measurable Z1, Z2. This gives 1. And finally, we need to prove 4 implies 3, which was the midterm question. Midterm question. Since we did a similar proof last week about product sigma algebras, I'm going to just give a sketch of proof for 4 implies 3. So 4, we have this property for sets in the pi system. And 3, we have this property for sets in the full sigma algebras. So how to pass from pi systems to sigma algebras? The idea was to use monotone class theorem and do it twice, because we have 2 pi systems and 2 sigma algebras. In the general case where you have n products, n pi systems and sigma algebras, you need to use monotone class theorem n times. So it is too much effort. That's why I specialize into case n equals 2. Okay, so what do? We fix some set in P2 and define, not P2, S2. Here it is S2, right? Define the collection of sets for which we have this property. So by 4, we have S1 is a subcollection of D1, because we are given that we have this property for every A1 coming from S1 and every A2 coming from S2. So we show D1 is a Dynkin system. This is what I'm going to omit, is a Dynkin system. Then, by monotone class theorem, sigma S1, which is F1, is in D1. And let's read what this means. So probability A1 intersection A2 is probability of A1 times probability of A2 for all S1 in A1 in S1, no, A1 in F1 and A2 in S2 or the full space. So next, fix some A1 in F1 and define D2, which is the collection of sets for which we have the same property. But now our variable is the second set. Here it was the first set. I forgot to put 1 here. Okay, same property. Now by the previous step, we have S2 is in D2, right? This is what we have, right? Because our A1 is fixed in F1, and we are saying that this is true for every A2 from S2. A2 from S2. And the rest is, again, routine, because show D2 is a Dynkin system. By monotone class theorem, sigma S2, which is F2, is a subcollection of D2. This means we have the property for all A1 coming from F1 and A2 coming from F2. And this is what we wanted to show. This is what we wanted to show because this is the definition, this is the property in number 3 here. Right? So this finishes our proof using monotone class theorem twice. So such a proof, just this way, without those details, would get almost full points in the exam, because showing that this is a Dynkin system is actually not very difficult, and you would just lose maybe 2-3 points at most. And if you show this being a Dynkin system, you could have just omitted the second one, because it is the same thing. You're just repeating yourself, right? It is just boring proof. But this is like the main ideas, the skeleton. So with this definition or characterization of independence of sigma algebras, we can also talk about independence of random variables. Independence of random variables in arbitrary spaces, in abstract spaces. So let x1, xn be random variables where E1 script E1, En script En are measurable spaces. So recall that we have this notion of sigma algebra generated by a random variable. Do you remember the definition of a sigma algebra generated by a random variable? What kind of events does a random variable generate? Can you tell me the form of an event about a random variable? What kind of events do we look at about random variables? So if I have my random variable xi, remember the events that we look at when we define the distribution of xi, right? Can you tell the form of an event? such an event about xi? A generic form?
Xi takes a value or something.
In somewhere, right? In some set, let's say di. So as di ranges in its sigma algebra, this is indeed a sigma algebra. You don't need to put a sigma here. This itself is a sigma algebra. We checked this. This collection is closed under countable unions and so on. So this is a sigma algebra, is the sigma algebra generated by xi. So our definition is now very easy because we're just going to define the independence of xi's in terms of the independence of their generated sigma algebras. So we say x1 to xn are independent if sigma x1 to sigma xn are independent. Okay, that's just a definition, but it gives us another way as a corollary to this theorem. So when your F1 is the sigma algebra generated by x1 and Fn is the sigma algebra generated by xn, you can rewrite this theorem in a different way. This is what we're going to do right now. This is going to be a corollary to this theorem. So corollary. Again, the following are equivalent. So number one is x1 to xn are independent. Number two is, so now I'm going to write down the definition of independence, okay, in this way. F1 applied to x1, Fn applied to xn, expected value of F1 applied to x1, F2 applied to Fn applied to xn for all positive measurable F1 from E1 to R bar plus and Fn from En to R bar plus. You can rewrite the same thing for all bounded measurable F1 from E1 to R and Fn from En to R. So I'm just rewriting the definition of 1 here, the meaning of 2 here, and now we're going to write down 3 and 4. They're going to become 4 and 5 here. So an event in F1 now is of this form, right? Of this form. So the joint probability that x1 is in D1, xn is in Dn, is the product of the marginal probabilities. Indeed, this is the definition of independence given in undergraduate courses, right? So we have it now. For all D1 in E1, Dn in En. And finally, you can specialize into the same thing. D1 in P1. Now I'm going to make them pi systems. Not the full set. This is the full set. This is the full set. D1 is coming from E1, right? En. Let me write here where P1 is a pi system such that it generates E1, and this is a pi system such that it generates En. They are on different spaces, on E1, on En. They are on the image spaces. And a final thing, so let nu be the distribution of x and nu I, the distribution of xi. So this statement says we have nu is the product of nu 1 to nu n. Okay? So the proof is very simple once you remember an important fact. An important fact. So remember that here we look at z1, that is f1 measurable. So zi from omega to r bar is sigma xi measurable if and only if what? So remember. If and only if what? So we talked about monotone class theorem for functions, and then as an application of that, we showed that some random variable is measurable with respect to the sigma algebra generated by xi if and only if it is a function of it. So being measurable with respect to the sigma algebra generated by xi just means that it is a function of xi, like square, like sine, like cosine, for some measurable function fi from ei to r bar. And moreover, if your zi is positive, so if zi is positive, we may choose fi to be positive. And if zi is bounded, we may choose fi as bounded. So with this, 1 equivalent to 2, equivalent to 3, equivalent to 4, equivalent to 5 is just rewriting the theorem. And 4 is equivalent to 6 follows since nu is determined by its values on measurable rectangles. So number 6 is about the full measure. Number 4 is about that joint distribution on measurable rectangles. But measurable rectangles form a pi system that generates the whole product sigma algebra. And we have a probability measure here. So it is uniquely characterized by its values on measurable rectangles. So there is almost nothing to prove here. You just need to remember this useful result. Okay? We haven't used it anywhere so far. This is the first time we are really using it. But that's by itself is an interesting fact. It's an interesting fact because it tells you the meaning of measurability. Measurability. So measurability sounds abstract to many people, but indeed, with this characterization, it is not very abstract. It is just a transformation of xi, some function of xi. Okay? Of course, when you square it, when you take absolute value, you lose some information. Okay? You lose some information because, for instance, if you're squaring, you treat the minuses and pluses in the same way. They kind of become the same thing when you square things. So the sigma algebra generated by this is smaller than the full sigma algebra here, but it is still a sub-sigma algebra. So the sigma algebra generated by zi is still a sub-sigma algebra of sigma xi. Okay? Okay, this is all I want to say today. Next Tuesday, we're going to continue discussing independence and also talk about Gaussian vectors. And that's going to be the end of this chapter.